Thank you. Thank you. So today I'm going to talk about a framework called Vero. It's a flexible and efficient programming abstractions for IRF research and production. So here's a brief overview. So I will first discuss some introduction and background about what is IRF, especially today with large language models, and how it's related to the traditional RL. And then I'll move to the motivation of how existing reinforcement learning infrastructures can solve this problem and when it cannot by analyzing some of the workloads of RLHF, especially when you're dealing with large language models. And based on those motivation and observations, I will introduce our framework, which is called hybrid flow. It's a core technique used in our framework that somehow combines the single controller programming abstraction with the multi-controller val array. And I will show you some programming APIs and examples. Okay? So when we move to the era of large language models, what we do is that, for example, the ChatGPT, so it goes through three processes. We first do we first do pre-training, that by crawling a bunch of data from the website, and then do pre-training via the next token prediction. And then we do supervised fine-tuning by using a lot of prompts and ask a lot of coworkers to write response, and then we just fit the response using the prompt. And there's a last step, which is called the alignment. That the goal of alignment is to align the values of the output of the large language model to the human values. So mathematically, what does it mean? It means that we want to decrease the probability of generating answers that are incorrect, that has hallucination, or it has some harmful to the humans. And we want to increase the probability of answers that are most likely chosen by the human beings. So here's the example that I just asked ChatGPT yesterday, that how to make a bomb. And so obviously, ChatGPT shouldn't answer this question and saying that, oh, here I cannot assist you, and here's why. And this is obviously a model that is aligned with the human values, because I'm pretty sure that in the pre-training, there's data on the website on how to make a bomb. Okay? And so RLHF is one of the approach of alignment. So in order to talk about alignment, we have to talk about language model generation as an MDP. So in order to use RL in this language model generation, we have to model it as an MDP. So here's another example that I asked ChatGPT to write a quick sort, and here it is its response. So actually, this language model generation is token by token. It can be actually modeled as an MDP. So the state is the prompt. The prompt is write a quick sort, and the current generated response. So the response of the generated by ChatGPT is not appear suddenly. It's actually token by token. So the state is the prompt plus the current generated response. And the action space is very simple. It's just the vocabulary size. And the state transition is that we concatenate the current state, which is the current prompt plus the generated response, and the action, which is the next token. And then this forms to the next state. And the reward in this, when we train language model, is actually computed by another language model called the reward model. And the terminal state is when the end of sequence token is generated, and then that's complete. And then the ChatGPT shows the output to the user, to the end users. So this is maybe a little bit abstract. So I will show you a concrete example. So here's state. We have write a quick sort, and then we put it, and then we just give it to the large language model. It output a probability distribution of the next token, and then we sample from that distribution, and the next sample, suppose, is here, and then we concatenate the here to the previous state, and it becomes write a quick sort here. And then we just send it to the large language model again, and it outputs the probability distribution of the next token. And then we just keep sampling until the end. The last token should be the end of sequence token. And then this sampling procedure ends. So as we can see, that it's actually a trajectory rollout using ARMs. And so this forms the state, the action space, the transition probability. And what we can define of the reward is that, so this reward is defined by this 2022 InstructGPT paper written by OpenAI. So for each of the intermediate state, the intermediate reward is the KR divergence between the current policy, which is the policy that used to roll out the trajectory, and the policy that is from the supervised fine-tuning, which at the beginning. So so in order to estimate them by sample, so it's minus beta times the log of the probability difference. And for each intermediate step, it's this, except from the last step, that we will have a reward R. So here there's a reward R minus the KR divergence. So this reward R comes from the reward model. So the reward model actually output a single scalar R, and it's plugged into the end of state state. I'm sorry, end of sequence state. And this reference and this pi reference is the model weights with the supervised fine-tuning. Okay, so this is forms a well-defined MDP, right? So another thing that I want to talk about is the reward model. So the reward model is basically that saying that there's another large language model, and I just give the whole sentence to the LLM, and it output a single value of saying that what's the score of this sentence, and it's actually trained by using ranking laws. We just form a lot of different pairs and then send it to the model, and train using ranking laws, and then the model will output a value saying that okay, how humans prefer this sentence, and we want to optimize the trajectory, which is the language model generation, such that the reward is maximized. So this form a well-defined Markov decision process that can be solved by any IR algorithm, such as PPO, which is done by the OpenAI at the very beginning. Okay, so yes, so as we can see that, so a large language model generation can be modeled as a well-defined MDP. So obviously there are some existing distributed RL infrastructures, such as RLib, that can actually solve this, right? So so there's an algorithm PPO implemented in the RLib, and can we directly use it to solve like RLHF? And the answer is absolutely yes, we can do it. So here's how we do it. We just so in the traditional classic RL, what we interacting with the environment is called the OpenAI gene. It's a real-world environment, and we just need to change it to the autoregressive generation using language models, and replace the MDP interactions with the real-world environment with language model generation, and also the reward function computed by the model. So so language model generation can be modeled as a model-based RL. So here, yes. So as we can see that we can simply solve this with existing infrastructures, but there are some problems with it. So there are many challenges when we actually apply RLib in real-world training. So one of the fundamental challenge is that the model size scales. So for classic RL, the model size is typically very small. It's just maybe 1 million parameters or 7K or hundreds of K parameters. But when we talk about large language model these days, it's about like Llama 8B, Llama 3.2AB, Llama 3.2, 90 billion parameters. It's huge parameters. It cannot even be fit onto a GPU. So so this means that this already implemented distributed data paradigm is actually not sufficient to train large models. So we have to use some model paradigm that trunk the model parameters into different GPUs. So there are several ways existing there. The first one is called tensor paradigm, and we have pipeline paradigm, and we also have the PyTorch native fully sharded data paradigm. There's a reference. So the tensor paradigm and pipeline paradigm originate from the NVIDIA's Megatron ARM repo. Okay, so that's the first challenge. So the second challenge is that okay. So the second challenge is that when we see these previous so what PPO does is that in the learners and the environment runners, there is a weight synchronization. So the runners and learners are on different machines, and each time the runners just fetch the latest weights from the learner. It's actually very natural when the weight is very small, right? So just send it through the Ray RPC, and then that's done. But this becomes intractable when the model becomes very, very large. So this is very slow when the model is getting large. So there are some numbers here. So for example, if we run on the NVIDIA's A100 RDMA bandwidth, which is 50 gigabytes per second, and then we are training Llama 405 billion parameters. So this takes like 1 minute just to transfer the weights. So this is basically unacceptable in a real-world systems, because when you do weight transferring, the GPU is basically idle. So the third challenge is that we actually want our framework that is flexible for research. And we actually noticed that nowadays people usually do direct preference optimization instead of PPOs because we believe that because the DPOs is very simple to implement just by tweaking the SFT procedure. So we believe that that's actually lack of infrastructures. And when we're building our infrastructures, we are considering that how can we make our infrastructures flexible for research. So when we analyze the nature of IR research, is that RL research doesn't typically care about neural network architecture. So for classic RL, it's just convolutional networks with LSTM. And nowadays, it becomes transformers. And RL research more care about RL data flows. So what is RL data flow? It's like, how do we sample trajectories? Is on policy or off policy? And how do we define loss function? Is it a Q loss? Is it a policy gradient loss? This kind of stuff. And we we take this in mind, that we want to feature this. We want to build our framework that is flexible for this kind of research. Meaning that new algorithms can be easily implemented, and our frameworks have to be modulars. Okay, so based on the challenges, we get some observations, and we'll introduce our methods. So there's a very high level and abstracted comparisons between there are two programming abstractions, which is called the single controller versus multi-controller. So Ray is one of the greatest demo of single controller. And single controller is also proposed by Google's Pathway in 2022 that is building on their pathway systems. And all those their gamma is actually trained using this pathway systems. And here I just show some high-level idea what is a single controller and what is a multi-controller means. So in single controller, there is a central control process and a list of workers. So the central control process doesn't do actually computations, and the list of workers do the computations. Each one of them holds a GPUs, hold a GPU, and the control process gives the workers instructions and data to compute. So instead of so the workers just have a set of computation APIs, just for example, forward and backward and optimizer step, and the control process give them the data and the instructions. So here's the example. So which is actually very similar to the IRLib. So suppose I have a single process controller, and I have a bunch of optimizers and workers that to play with. So in order to do one of the gradient optimizations, what we do is that we first, the single controller orders this, give instructions to all of the workers that first set the optimizer gradient to 0. So this is written in PyTorch. And then we trunk the data, and then we send this data shard to each worker. And then each worker does the forward and backward, and the single controller aggregates the gradients and then the main model on the single controller applies the gradients. So that's that's what the single controller code looks like. So the benefit of this approach is that it's very flexible, because it's just every program is defined by this single process controller that I can do anything. I don't need distributed things, because the distributed things is handled by the workers. I don't care about this, and how the distributed things of the workers is done by the PyTorch. But there's some problem with it, is that I have to send the data and the instructions to the remote. So there's large dispatch overhead. So on the contrary, what multi-controller does is that I have a list of workers, and there's no central control process. So, and each workers execute the same program using different chunk of the data in a batch, like an SPMD style. And it's very fast, but it's less flexible, because each workers have to execute the same code with just different chunks of data. So here's the example. On each process, what we do is optimize the zero grad and then forward, backward. And then what we do, and then how do we communicate between different workers is via Nico. It's NVIDIA's collective communication library. Okay. So based on this previous two key observations, what we actually observe is that when we scaling traditional classic RL to RLHF, in which case the central difference is just the model size scales significantly, and then the data flow problem of classic RL becomes two-level. So we have the data flow of RL, which is mainly cared about by the RL lib. It controls how data is computed and exchanged among different components in the RL systems. And then since the model becomes very large and distributed training is necessary, and there's another level of data flow which is called the computation workloads of the large language models. And we actually observed that most of the open source LLM computation workloads are implemented using SPMD program, which is multi-controller. So due to the performance issues. Okay, and this workloads actually has three primitives in RHF. First, autoregressive generation, just like what VRM does and S3Long does. It's just autoregressive generate tokens, and also LLM inference. We just have a forward pass, and also LLM training. Just give them a batch of data, perform forward, and then perform backward, and then optimize the step. So each of the primitives is actually done in a distributed fashion. Okay. So this comes to our design, which is called the hybrid controller. So instead of so the overall idea is that we want to make the RL data flow as simple as possible, and we don't want to use multi-controller for many point-to-point, more-to-more communications. We want to use a very single process to implement the whole RLHF data flows. But we actually want to use multi-controller to implement the computation data flows, like with existing LLM infrastructures such as VRM and PyTorch FSDP. And we don't reinvent the wheel. So the core idea here is that the single controller has to manipulate the computations encapsulated by a multi-process controller as if it's a single process. And this is the core of the design. So the idea is that the computation is done by many workers, but their APIs but their computations runs in an SPMD fashion that can be encapsulated as if it's a single process. And this single process can be controlled by the reinforcement learning data flow. And I will show you some examples later. So, in order to implement that, we need a core data structures. Okay. So here comes to the implementations. So we have to introduce a data structure called the worker group. And inside the worker group, all the process runs the same program, SPMD. And expose APIs that can be called as if it's a single process. So I'll show you an example. So suppose I'm writing a Llama style FFN, fully connected layer in the transformers, and I have 4 GPUs. And I'm running tensor parallelism plus data parallelism. So there are 4 ranks. And I have input batch. And then I dispatch. So the input batch is on the single controller. And what we does is that I want to trunk the input batch into 4 of them. And each of them send to each workers. And then these workers do some computations in SPMD fashion, and then get the distributed outputs. And then the single controller does is it gathers output and form a new batch. So and this is internally is a worker group. So so from the outside point of view, it doesn't really care about what's inside. What we does is we give them a batch and we launch some APIs for some computations that is done distributedly, and then we get the output. Okay, so and here is the code that can do this. So we define a class called the FFN workers, and then there are 3 layers. Gate it's a llama style FFN. It has gate up and down, and then it has an infer function which is forward. So internally, it is very, very similar to a single process, and then the ladder code runs. So the code after this runs on the single controller process. It's just one process, and the above and the remote code is actually distributed. There are 4 of them running the same code inside this reworker group, and so what the infer does is that we give them X, and the X is automatically trunked into 4 parts, and each part is sent to each worker, and the workers do them in a SPMD fashion. And after this is done, the answer is gathered from all these workers, and then aggregated on this single controller. Okay. So here is the process of data dispatch and aggregation. So the data dispatch and aggregation is performed by the worker group. So and we actually know all of the information, such as tensor parallelism size and the data parallelism size of the worker group. So so in large language model training, so the data has to replicate among the TP groups and trunked in the batch size of the DP groups. And here is that we can, so X is some data on the single controller, and we just trunk it and then into a list, and then we just dispatch all of them to the distributed workers. And then after that, we just collect all of the data from the distributed workers. So this idea is that these distributed computations can be encapsulated, and it can be invoked by a single API from the driver. I mean, from the single process or the driver. Okay. Now, based on this idea, we just built a framework for IRF. It has 2 main components. The first is that we build a hybrid controller library upon Ray by introducing some core data structures called workers and a Ray worker group. And each process is managed by a Ray remote process. And different Ray remote process form a worker group. And we use this library to build different RLHF components like actors, rollout, critic, and reward models. And here is the basic APIs. Let's go through it. So we have actor. It has 3 APIs: compute log prop, update policy, and generate sequences. And each one of them is actually running in an SPMD fashion internally, and it can be invoked it can be invoked by the single process externally. Okay, and we have the same as the reward model and reference policy, and also critic. Okay, so the underlying implementation that can be fit into this APIs is actually depends on the distributed frameworks. For example, this generation we actually use the VRM, and for training and inference you can use the Megatron ARMs or FSDP, PyTorch FSDP. Okay, so after building this, after building all those computation components in SPMD fashion, we can actually invoke this SPMD, invoke those computation components by using a single process controller. So what we does here is very simple. This is run on a single process. So what we do is like just for the data, for each problem batch in the data loader, and then what we do is we just generate a sequence or trajectory routes, and then we compute the value, compute the log probability, compute the reward, and then we compute the advantage, and then we use the advantage to update the actors and then the critics. So this becomes very natural after we define these worker groups. So from a single process controller point of view, it doesn't actually care about how data is split or replicate. Under the hood, the worker group has to take care of this based on the model and data parallelism strategies. So from this high-level point of view, it's just a single process that has nothing knowledge about the underlying data or data and model parallelism strategies. Okay, so next we want to highlight one of our core design in RHF systems that to tackle the problems of weight transfer. So the weight transfer between the rollout and the training is very heavy, is very time consuming. So we want to avoid as much as possible. So here, what we do is that we will actually want to share the weights of the rollout, which is generating those sequences, and the weights that is during training. So what we do is that we want to perform model parameter resharding during the runtime. So here example that if we're training using FSDB03, and then we want to if we do rollout in VRM, it's actually the parameters is actually sharded in TP. So there has to be a data resharding process here, and we actually design a very simple APIs for this. So it has a sharding manager called the FSDP to VRM sharding manager. What it does is under the hood, it performs weight resharding from the FSDP. From the FSDP form to the tensor parallel form. And what it does under the hood is that it's just some PyTorch D-tensor redistribution. So by using the simple APIs, we can perform two different computations using the same set of weight parameters. Okay, so just give you some experimental results. So by using these APIs, we can easily implement a bunch of PPO variants, such as Remax, Safe IRHF, or group-related policy optimizations with a few lines of change. So for the GRPO and the Remax, we just simply remove there's no critic, and it estimates the advantage using a different way. So what it does is that we can simply remove critic and then change how the advantage is computed. And for Safe IRHF, it deploys multiple reward models, and we can simply add reward model worker groups for another set of reward models, and then call the same API on this single process, and then we can combine the rewards in some way that can be that is in the research paper. Okay, so we also compare the performance that is achieved by some open source implementations, such as DeepSpeed Chat and OpenIRHF. It shows some great improvement. Actually, this is we submit a paper to our paper is actually accepted by the EuroSys 25, and here's the archive link if you want to have some more details. And our code base will open source soon, so. It's undergoing the company's internal review, and I know this topic is a little bit abstract and heavy, so feel free to ask any questions. Yeah.
My question is, how do you take care of environments where the experimentation is being run on? Let's say if you are doing a
So in the RLHF, the environment is basically the language model itself. So it's generating So if we look at the very beginning, there's a definition of MDP. So
I think my question is this specific to, can it be only used for large language model, this framework, or can be generalized to some other use cases too?
It particularly solves reinforcement learning in large language models because it just presents unique challenges. It cannot be used in like classic RL gaming or whatever. Because in gaming, the problem is how do we accelerate the environment, and the model there is very small. And here the challenge is quite the opposite. The environment is very simple, but the model is huge. Yeah.
Does the later part of the equation converges to 0?
Later part of the equations. So which?
Talking about the beta log. You have like the first part of the equation minus the second. Does it converges to 0?
Actually, this is a per step reward. It's not it's not an equation. So this is a pre-step reward function.
But as it keeps on going from S0 to ST, does it converges to 0?
This is the state. So S0 is the current output from the language model. It's a output. It's not a number.